Have you ever seen one of those huge collisions in ice hockey and just wondered, what's the physics behind that? Well, today, we're going to break one down. We'll use a classic exam question to really get into the forces at play. Okay, so let's set the scene. You've got two ice hockey players, and they're about to have a really bad day. Player A, he's a bigger guy, 7-8 kilos, and he's cruising at 7.5 meters per second. Coming right at him is player B, a little smaller, 51 kilos, but still booking it at 5.5 meters per second. And here's the kicker, they're going to collide and stick together. So the big puzzle for us is where do they end up going and just how fast are they moving?
Now, before we can solve this, we've got to talk about a huge, fundamental rule in physics. I mean, this isn't just for hockey players. This principle is behind every collision in the universe, from tiny particles all the way up to planets smashing together. So, the exam question kicks things off by asking, what does it even mean for momentum to be conserved? And trust me, this isn't just some boring textbook phrase. It's literally the key that unlocks this entire puzzle. So, what does it mean? Okay, here's the big idea. In what we call a closed system, and don't worry, that just means we're ignoring stuff like friction on the ice for now, the total momentum before the crash is exactly the same as the total momentum after the crash. Think of it like this. Momentum can't just vanish into thin air. It has to go somewhere. It just gets passed from one player to the other. All right, now that we've got that principle down, let's put it to work. Let's see how this one powerful idea helps us figure out exactly how fast these guys are moving together right after they collide. Okay, first things first. We always have to figure out the total momentum of the whole situation before the collision even happens. So we'll calculate the momentum for each player separately, and then we'll just add them up. And remember, the formula is super simple. Momentum is just mass times velocity. Now pay close attention here, because this is probably the most important part of the whole calculation, the plus and minus signs. Momentum has a direction, right? So we have to show that with our numbers. Let's just say player A's direction is the positive direction. That gives him a momentum of plus 585. That means player B, since he's coming from the opposite way, has to have a negative velocity, and that gives him a momentum of minus 280.5. If you mess this up, the whole answer will be wrong. It's absolutely critical. So what's the total momentum before the crash? We just add our two numbers together, 585 plus that negative 280.5. And that gives us a grand total of positive 304.5 kilogram meters per second. And see that positive sign? That's super important. It's already telling us that the overall motion is going to be in player A's direction, to the right. And here's where that conservation principle comes back in. If the momentum before was 304.5, then the momentum after has to be, you guessed it, 304.5. Now, after they hit, they're stuck together. So we add up their masses to get a new total mass of 129 kilograms. So now we just have to rearrange our little momentum equation to find that final speed they share. Okay, time for the final calculation. We take that total momentum, 304.5, and we divide it by their new total mass, 129. And what do we get? Boom, there's our answer, a final velocity of positive 2.36 meters per second. And that positive sign proves it. They both slide off together, to the right. Pretty cool, huh? Okay, we're done with the math. Now for the last part of the question. This isn't about numbers, it's about something way more important. How physics actually helps keep these players from getting seriously hurt. So you see all that bulky padding they wear, right? Why does it actually work? I mean, it's not just about being a soft cushion. The physics behind it is actually way, way smarter than that. It's this amazing three-step chain reaction. First, the pads compress. That simple act of squishing actually increases the time of the impact. It stretches the collision out over a few extra milliseconds. And here's the physics magic. Force is just the change in momentum divided by time. So if you make the time bigger, the force gets smaller. A smaller force means less injury. It's that simple, it really is. The key is to increase the time, because more time means less force. Remember that. All right, so let's do a super quick recap. What are the big ideas you absolutely need to remember from all this collision physics? Okay, two things. Number one, the law of conservation of momentum. It is your best friend for solving any collision problem. What goes in must come out. The total momentum never changes. And number two, impulse and force. That relationship between time and force is everything when it comes to safety. You stretch out the impact time, you slash the force. Simple as that. And that leaves us with one final thing to think about.
This whole increase the time to reduce the force thing, it's not just for hockey pads, it's everywhere. Think about the crumple zones on a car, or an airbag, or the soles of your running shoes. They all do the exact same thing. So my question to you is, where else do you see this brilliant bit of physics at work? It's all around us, quietly making our world a whole lot safer.